This is VLSI data conversion circuits, lecture 58. In the last class we were trying to understand the effects of DAC nonlinearity in continuous time delta sigma modulators, and we saw that if there is mismatch in the DAC, then the levels are not what they are supposed to be, and that causes a rise in the in-band noise floor as well as harmonic distortion. Now, we were discussing that the phenomenon may be understood in the following manner. We saw that in this particular example of a 4 level DAC, the sequence at the output of the modulator is decomposed into a thermometer code represented by T1, T2 and T3, and by definition or by construction T1 plus T2 plus T3 equals V, alright, and therefore one can see the operation of the thermometer DAC in the following light, that the DAC is essentially decomposing the input signal V nonlinearly into 3 subsequences, right, T1, T2 and T3, converting each one of these subsequences into a waveform and adding the waveforms up. Now, since T 1, 2 and 3 are related to V in a nonlinear fashion, perhaps by curves shown here, right, it stands to reason that the spectra of the signals T1, T2 and T3 will look like this. So, apart from shaped quantization noise in the input signal, they will consist of harmonics of the input signal plus the in-band noise floor, which will be or which can be expected to be considerably higher than what was there in V to begin with. And the reason is that thanks to this stiff nonlinearity, frequency components out of the signal band will mix with each other and fall in band. Okay. Now, if T1, T2 and T3 were weighted with exactly the same factors, right. In other words, since by definition V is T1 plus T2 plus T3, it follows that the pass spectral density of V must be the same as the pass spectral density of T1 plus T2 plus T3. So, what is actually happening is that even though the individual signals sequences T1, T2 and T3 are horribly nonlinear functions of V, when you combine them together with the same weights, then all these harmonics are cancelling out, and so is the in-band noise floor, right. So, that you are actually left with the true spectrum of V. So, now it becomes quite easy to understand why, when there is mismatch in the elements, there is both an increase in the noise floor as well as harmonic distortion. Signals which were precisely supposed to cancel out each other's harmonic components are slightly mismatched because of the passive element mismatch. I mean, resistors are off or capacitors are off or transistor current sources are off. So, when they are combined, the factors with which you combine them, for example, can be, say, what you are actually combining is 1 plus alpha into T1 plus 1 plus beta into T2 plus 1 plus gamma into T3. So, you can interpret this as T1 plus T2 plus T3 gives you your desired signal, but these culprits do not really cancel out. So, you are left with some remnants, and So, you can expect that there will be residual uncancelled distortion components and some residual uncancelled noise flow, right. So, in the signal band when there is mismatch, you can expect a noise floor as well as some uncancelled distortion. Does it make sense? All right. Okay. Now, so to prove this point, as I mentioned to you earlier, I think this is not very cleanly visible. If you now assume that each of the resistors are 3R by 1 plus delta 1, 3R by 1 plus delta 2 and 3R by 1 plus delta 3, then the currents will be Vref by 6R times T1 times 1 plus delta 1 plus T2 plus times 1 plus delta 2 and T3 times 1 plus delta 3, and clearly delta 1, delta 2 and delta 3 are not known a priori. Okay. And therefore, when you combine these three signals together, you find that in the presence of mismatch, the spectral density actually looks like this. So, this is the red curve which is the PSD with mismatch, and these are the PSDs of T1, T2 and T3, and this is what one would have got if the weights were precisely equal to 1. All right. Okay. So, now we have a hang of the problem, right, and we are trying to figure out how one can solve this. All right. So, what is the, within quotes, what do you think is the most straightforward way of doing this? Of course, one thing is to say, okay, hey, if I somehow figure out delta 1, delta 2 and delta 3, right, and go and cancel them off, then this will be quite okay. So, in other words, this is what is called calibration of the DAC, where you take, somehow measure the mismatch between unit elements and somehow vary the unit elements so that they are all equal. Okay. A common way of doing this is to say, let us say this is a simplified equivalent of a current source. So, assume there is biasing and all this stuff. Okay. Now, clearly because of device mismatch, the actual current is not I1, but it is I1 times, or it is not I, but I times 1 plus delta 1. So, in principle what you can do is, you know that you wanted it to be equal to I, correct. So, what you can do is you compare it, let us say you have a master current source which is equal to I, right. You compare it with I and you add the, it is actually I into 1 plus delta 1. So, you know that it is off by a fractional value of delta 1. So, if you had an auxiliary current source, I found an auxiliary current source, right. So, this is VB and VC, these are fixed. I have some variable current source, I compare, use an op amp and compare this current source with a master current source, all right, and tweak this variable current source such that the two currents are equal, all right, and somehow I must have some way of storing that information, is not it. So, in other words, this must provide the minus delta times I. Okay. Now, this is a multi-bit DAC, so obviously there will be many current sources. So, you compare every current source with the same master current, cycle through all the n current sources that you have, store how much each current must be corrected by, and once you finish the calibration cycle, in principle you have a DAC which is mismatch free, right. I mean, this is what you call a brute force way of, I suppose not quite as brute force as simply making the current sources bigger, but this seems like a fairly straightforward way of solving the problem. So, this is done sometimes where the DAC is calibrated. Of course, you have to worry about now when you calibrate the DAC, because when the DAC is being calibrated, obviously you can't use the modulator, right. So, this must be done in the, either you have a separate phase where the modulator is not being used and that use that time to calibrate the modulator, or you can do it at power up, right. So, when you power up the whole chip, for some time you will not have the modulator in action because all these calibration loops are running. Okay. The next technique right. So, as you can see, what we want to do, right, is for a change not match fixing, but mismatch fixing, right. You need to get rid of the problem, and as you will see, it is indeed possible to do it without any knowledge of the deltas, right. It would seem, at least on paper at first sight, that if I knew the mismatch values, then perhaps there could be some way of fixing them, correct. But as we will see, quite surprisingly, it is possible to get rid of this mismatch error to a large extent, even when you do not know these mismatches a priori. all right. So, and the problem, as we have all seen, is that with mismatch, why is there an increase in the in band noise floor and distortion? Because we are separating the, I mean, see, we can't avoid the fact that we are going to add the outputs of several unit element DACs, correct. Now, the problem is that if the weights are perfect, then when you add the outputs of these unit element DACs, you know, all the distortion components magically cancel out. However, the problem is that when these weights are not known, or there are slight errors in these weights, the cancellation is not precise enough, you understand. So, if you want to be able to add these things with slightly imprecise weights and still not see harmonics or an increase in the noise floor or such a drastic increase in the noise floor, what do you think you can do? What is the problem? The problem is that we were separating the input V into 3 sequences, each of which controlled one of the unit elements in a nonlinear fashion. Okay. The moment you pass the signal V through some kind of nonlinear function, the result is bound to have harmonics and an increased in band noise floor. And no surprise that when you combine them, you know, with the wrong weights, you will see residual distortion and noise. So, if one was able to separate them linearly, right, in other words, make T1, T2 and T3 linear functions of V, then one would be able to the individual sequences would have no harmonics. So, when you add them, you are not relying on cancellation, you understand, okay. You are not relying on cancellation. So, if the weights are slightly off, you do not see any distortion, you understand, okay. So, let us see what all we can do. The first historic technique that people used is what is called dynamic element randomization. Again, I will use a 4 level DAC example. So, there will be 3 unit elements, okay. So, each one of these rectangles corresponds to an element. If an element is being used, it is shaded in red, okay. So, if you had a conventional thermometer DAC, when V was 1, we choose one element and we choose the same element regardless of how many times V equal to 1 occur, you understand. So, this would reflect the choices of unit elements, and on top I have plotted I have marked the error with respect to the ideal should have been 1, it is actually 1 plus delta 1, and the error will be delta 1 always. On the other hand, if V was 2, the error will be delta 1 plus delta 2. since delta 2 is not the same as delta 1, clearly this is a, I mean using a thermometer is a nonlinear process, because the input is doubled, but the error sequence has not doubled, because delta 1 is not equal to delta 2. Is this clear? Okay. Now, dynamic element randomization is a strategy where you say if v equal to 1, there are clearly how many ways of picking one element from 3? There are 3 ways of excuse me, there are 3 ways of picking one element. So, all that one says is that, hey, I am going to pick at random every sequence, I mean at every instant of time, I am going to pick any one of these at random, alright. So, in the first instance of time I pick the third one, second instance I pick the first, and so on, and the error sequence now is it is clearly different for each instance, and you can see that it is delta 3, delta 1, delta 2, delta 2, delta 3, delta 1, and so on. Okay. But what I want you to understand is, can you comment on T1, T2 and T3 in the conventional case versus the randomized case? How does the sequence T1 look like here? It is always 1, while T2 and T3 are 0 always. Okay. What about here? So, this the T1 sequence here is 0, 1, 0, 0, 1. The T2 sequence is 0, 0, 1, 1, 0, 0. The T3 sequence is 1, 0, 0, 0, 1, 0. All right. Of course, the way I have drawn the diagram here, it also appears as if in for this small sample, the average of T1 is
same as T2.
What is the average of T1? 2 by 6, which is 1/3. The average of T2 is 2 by 6. The average of T3 is also 2 by 6. Okay. So, at least it seems as if T1, T2 and T3 are linearly dependent on V. Understand? Because the average of T1 is the same as, I mean it has to be if the sum of T1, T2 and T3 have to be equal to V, it must follow that the average of T1 plus the average of T2 plus the average of T3 must be equal to V, correct. So, apart from a scaling factor, the average of T1, T2 and T3 are proportional to V. Okay. When you can make this, you can come to this through another argument, right. For a fixed V, right. So, if you look at only the rows here, right, the probability that a particular cell is red is what? Is 1/3. Okay. So, in other words, T1 for example is 1 with probability with probability p, which in this case is basically v by n level minus 1, correct, all right, and is 0 otherwise with probability 1 minus p, correct, because at every instance of time you are choosing this, you are picking whatever, in this particular case 1 cell out of 3 cells, all right. So, what is the average of, what is the expected value of T1? It is simply P, which happens to be V by n level minus 1, okay. Similarly, so E of T1 is P, all right. The autocorrelation, and let us remind ourselves that P is nothing but V divided by n level minus 1. What is the autocorrelation of the sequence T1? Is the expected value of T in the mth instant and T in the nth instant, all right, and this must be equal to please note that at the mth and the nth instants the decision of which to choose is completely independent of what happened earlier, correct, because the choice is purely random. Now, that means that this E of the expected value of Tm times Tn, what is the probability or rather the probability density function of Tm Tn is what? This will be 1, this can also take on only Tm times Tn, what values can this take on? 1 or 0. So, this is 1 with probability what? When both of them are 1, and that happens with probability p square, right. So, Tm Tn is 1 with probability p square is 0 with probability 1 minus p square, correct. So, what is the autocorrelation function? So, R T T of m comma n is nothing but simply the expected value of Tm Tn, which is p square. Okay. This is for m not equal to n. Okay. For m equal to n, what is it? It is simply p for m equal to n. Clearly, this does not depend on m or n, or you can see that the cross correlation does not depend on the autocorrelation does not depend on m or n. So, you can as well say that this if you look at the autocorrelation function, you can now plot it simply as a difference between m and n, right. For 0 it will be p, and for n not equal to 0, you will get p square. Does it make sense? So, how will the PSD of this look like? How is the autocorrelation related to the path spectral density? Fourier transform. This is a DC sequence plus an impulse. The DC sequence will give you an impulse at the origin, correct, and you will get right, and you will get a white noise component. Does it make sense? The DC component corresponds to the input signal, correct. You understand, that is P, sorry, P square, right, that corresponds to the square value of the input signal, all right. Along with it there is a white component. Does it make sense? So, this is the input and this is a white component. Please note that we have still not talked about mismatch at all. This is simply the transfer function, or sorry, this is simply how T1 relates to V. Okay. Now, please note that whether you are doing the conventional type of element selection or whether you do random element selection, always T1 plus T2 plus T3 equals V. You understand? So, it must follow that if the weights are exactly 1, right, whether you decompose the signal using the conventional thermometer decoder or whether you randomize the selection, if there was no mismatch, the PSD of T1 plus T2 plus T3 will look exactly the same and will be equal to that of V. Is this clear? So, okay, the only difference between randomization and the conventional way of choosing T1, T2 and T3 is that now all the drive signals T1, T2 and T3 are linear functions of V, right. I mean, we have just seen, in fact, this is not rigorously it is not rigorously proven that they are linear functions of V. All that we have seen is that the mean of T1 is the same as V, I mean V by 2 within a fraction, right, and we have seen this only for DC. Okay. All right. Now, without getting into too much mathematical detail, it now follows that if V is varying slowly by the same argument, okay, you can expect the, what can you expect for the mean of T1? If V was DC, the mean of T1, T2 and T3 is the same as, is whatever V by n, n level minus 1, correct. So, intuitively all the 3 paths are contributing to the output, right, regardless of whether the signal V is small or large. You understand? This is completely in contrast with the conventional thermometer way of decoding, where if the signal is small, only T1 contributes, right. If the signal is, I mean T3 gets into the act only when the signal is very large. Okay. All right. So, what I wanted to point out was that the spectral content of T1, T2 and T3 consists of the mean of V. We saw this for DC, and now it stands to reason that if V was varied slowly, the mean of T1 would also track V, right. I mean if V was 1, the mean of T1 is 1/3. If V was 2, the mean of T1 will be 2/3. So, if V change slowly over time, then it follows that the average value of T1 will also slowly track the average value of V. Does it make sense? Okay. So, since the individual drive waveforms have spectra which will therefore look like, let us say the input V was a sinusoid, you will expect that what will be the spectrum of the drive waveform of spectrum of T1 for instance. Okay guys, if the input is DC, this is the PSD of T1 or T2 or T3. Now, if the input was varying slowly, that means as a sinusoid for instance, what will be the spectrum of T1, T2 or T3? You can expect it to be the sinusoid, right, plus white noise. Okay. All right. I mean, this is the two-sided spectrum I have drawn, but what we have seen in the diagrams all along is something here, correct. All right. Now, if T1, T2 and T3 were combined precisely with weights of 1, what will the resulting spectrum look like? It will look like, if you still did T1 plus T2 plus T3, you should get something like this, correct. However, if you combine them with slightly different weights, what will you get, or what do you expect to get? Okay. Earlier what had we seen? You would see harmonics and noise floor increase. Why would you see harmonics? Because the individual spectra of T1, T2 and T3 had harmonics. So, when they are not added together in precisely the right way, there will be some residual harmonics left. Now, what do you see in the spectra of the individual drive waveforms? There are no harmonics. So, even if you add T1, T2 and T3 with slightly erroneous weights, one thing you can be sure about is that there will be no harmonics. Is this convincing? Okay. What about the noise floor now? So, if they are added with precisely the right weights, the noise floors will also cancel off, because by construction T1 plus T2 plus T3 always equals V, correct. However, if these are not combined in exactly the right way, one can conclude that instead of seeing the spectrum of V, you will also see in addition some uncancelled residual noise, which happens to be white, right, because the individual drive waveforms have spectral characteristics which are the input sinusoid plus a white component, which means that if there is mismatch and they do not cancel perfectly, some of that residual white component will show up in the output, alright. And clearly, as the mismatch becomes smaller and smaller, this residual white noise will become smaller and smaller. So, the total noise in band is the sum of the quantization noise of the modulator plus this uncancelled residual white component. If the mismatch is very small, you might be dominated by quantization noise and you have nothing to worry about, right. But as the mismatch becomes larger and larger, the white one will dominate and you will be worried about it, alright. So, the key point behind randomization, as you can see, is that it converts the sinusoidal tones into white noise, okay. So, this is a simulation showing the spectra of, there are 3 PSDs here and they are that corresponding to, let me show you, T1, T2 and T3, alright. One thing you can you should observe is that, even though it is not very clear here, it turns out that what is that component? That is the signal component in T1, T2 and T3, and that happens to be the same for all the signals, and that makes sense because each one of the drive signals is linearly dependent on the input in the same way, correct. So, the signal components better be the same. In fact, you can see that the PSDs of all the 3 drive waveforms is the same, alright, which I think I should draw your attention to the earlier waveforms, okay. So, I think you are not able to see it, but for instance, look at this harmonic here. These are the PSDs of T1, T2 and T3, and clearly you can see that each of these harmonics, the peaks are different, and that makes sense because the 3 nonlinearities are different, okay. And the signal components, in fact, you may not be able to see that here, but the signal components here are also different, okay, alright. So, this is the case where a regular thermometer DAC was used. In contrast to that, notice that when you do dynamic element randomization, you have the same spectra for all the 3 derived waveforms, and when you combine them again, this is with the same 5% mismatch that I had been using earlier. You can see that the residual noise floor is down, but clearly you are still way over the quantization noise, because the mismatch is apparently too high. You understand? Now, let us say I reduce the deviation. So, let us say this corresponded to some delta 1, delta 2 and delta 3. So, if I magically made delta 1, delta 2 and delta 3 lower by a factor of 10, what do you think will happen? The noise floor will go down by how much? In the I mean 5, 10, 20, the waveforms, the difference in the error waveform has gone down by a factor of 10. So, error power has gone down by a factor of 100, but you are plotting past spectral density. So, it should go down by power by a factor of 100, 20 dB, right. So, if this was like this and right, if delta magically became down by a factor of this thing, you will see that you should go down by 20 dB, all right. So, this corresponds to 5% sigma mismatch. So, clearly 5% sigma mismatch is not good enough, correct, because the noise due to mismatch is way higher than the quantization noise flow, right. It is about 40 dB, let me say about 30 dB worse, correct, and a sigma of 0.5% is also not quite as is not quite good enough, because you will see that you are still about 10 to 15 dB above the quantization noise floor. So, if I reduce this by a further factor of mismatch by another factor of 10, you would see something like this, then you will be dominated by quantization noise here, and then again you will see this notch getting filled up and you will see this, all right. So, in other words, in order that you are not limited by noise due to mismatch, right, in this particular scheme where which is called dynamic element randomization, you need a raw matching of 0.05%, that is what this is telling. All right. So, please note that even though you have only a 4 level modulator, in other words the quantizer is only 2 bits, but to achieve good SNR, the linearity of these DAC steps must be very high. You normally think that a 2-bit quantizer is a within quotes a very cool affair, right. You just need 4 steps, okay, and which means that in principle to get half an LSB of DNL, the elements can vary whichever way you want and you will still be able to get 4-bit linearity, right. But this is saying that 4-bit linearity, even though to get 2-bit linearity, even though the quantizer is only 2 bits, the linearity of this quantizer must be very, very good. I mean, this is like at the 12-bit level. Okay. 0.1% is 10 bits, right? This is of the order of 11 bits actually. You understand? Okay. So, you should go home with the feeling that, hey, you know, sigma delta is a way of taking absolutely lousy quantizer and getting fantastic resolution. That is true. However, when you have multi-bit operation, you must bear in mind that the feedback DAC, even though there are few elements, the matching between those elements is actually quite critical. If you were only, I mean, if you did just the normal thing of just depending on matching. Okay. In the next class, we will see that anyway, before I let you off today, let me conclude with this slide. This is with randomization, and this is with a normal thermometer decoded DAC. Okay. And what you can see is that this randomization has significantly eliminated tones at the expense of an increased noise flow, right. So, now the question is it possible to decrease the noise floor also? Okay. So, if you want to reduce the noise floor, I mean, basically what you are doing is you are combining 3 signals, right, T1, T2 and T3, all right. If the PSDs of T1, T2 and T3 are, I mean, they have the signal component of course, but if the so called, you know, the other component, the non signal component in the case of randomization was flat. Okay. If you want it to be, if you want a much lower noise floor, what can you say about the spectra of the individual waveforms that you are adding? If you combine them, okay, and you expect to see very little noise in band, it must follow that the individual PSDs, before you add them, correct, the drive waveforms of the individual or rather the PSDs of the individual drive waveforms must have very low noise floor within the signal band at least. Okay, if they have low noise floor elsewhere, you know, it is not of our concern. Definitely in the signal band they must have very low noise floor, so that when you add them up, even with mismatch, the fact that they have inherently low noise floor means that mismatch will no longer be a problem. Okay. So, we will see these techniques in the next class. So, we will stop here for today.